Hi everyone, welcome to the fifth lecture of Chapter 10. This will be our last lecture in Chapter 10. We are going to cover molecular orbital theory today. So far we've talked about molecule shapes through VSEPR, we've talked about valence bond theory, and so now we are going to talk about our last topic, molecular orbital theory. And the goal of molecular orbital theory is to describe molecules in a similar way to how we described atoms. So that's in terms of orbitals, orbital diagrams, and electron configurations. So now we're going to take, all of those topics that we used, when we described atoms, we're going to describe, molecules in that same way. This is actually, more how we depict molecules, in higher levels of chemistry. And so this will be kind of just an introduction to molecular orbital theory. You will definitely need to know this stuff, though, if you go on and you take, inorganic chemistry later in college. This molecular orbital theory will be kind of a central theme in those classes. So orbital mixing. When atoms share electrons to form a bond, their atomic orbitals mix and we form molecular bonds. Like that's what we've been talking about with that orbital overlap, right? Those hybrid orbitals. In order for these orbitals to mix and form that bond, they must have similar energy levels. They need to be able to overlap well, and they need to be close enough together, right? It's not going to make, your atom is not going to make a bond with another atom that's really far away in your molecule. They need to be fairly close in proximity. So this picture is an example of orbital mixing. The two atoms are both sharing one electron each for a total of two, and they're always going to be valence electrons. In this case, because we're drawing them as circles, these are both 1s orbitals that are overlapping and sharing those valence electrons. So these are both hydrogen, right? Each one has one valence electron. We share them, and now we have our complete duet. Each hydrogen has two valence electrons. So the molecule in molecular orbital theory is viewed on more of a quantum mechanical level. It's a collection of nuclei surrounded by delocalized molecular orbitals. Remember that we were thinking about electrons in terms of being both, a particle and a wave. And so molecular orbital theory starts to take into account the fact that electrons can be both particles and waves, whereas kind of our other theories about electrons or theories about bonding thus far have treated electrons kind of solely as particles. So we take these atomic wave functions and we kind of add them up to obtain molecular wave functions. So again, this is just an introduction to molecular orbital theory. You will get much farther into this if you go farther on in chemistry. So here, this bullet point says, recall an electron in an atomic orbital can be described as a wave function using the Schrödinger equation, which we didn't directly talk about in class. Again, that's one of those, you're going to need some Calc 3 and quantum mechanics when you get there to use that equation. But in general, we can describe them as a wave using this equation that Schrödinger came up with. And the waves have positive and negative phases, right? When we think about a wave, they look like this. We can think of these as being, the positive, and these being as kind of the negative below the plane. To form these molecular orbitals, the wave functions of the atomic orbitals combine. So each atom has its own wave function, and when we form, molecular orbitals, those two different wave functions of the atoms will combine to form a molecular wave function. And how the phases combine determines the energy and type of molecular orbital that's being formed. If the wave functions reinforce each other, so like if we have two crests or two troughs, maybe they're in phase, right? Maybe they're like this. They will get added together. That's what I mean by reinforce. Then we're going to form a bonding molecular orbital. This will be a region of high electron density existing between the nuclei. If the wave functions are out of phase and they kind of cancel out, so rather than being, looking similar where the crests line up and the troughs line up, maybe they've, done like this, right? So that would be the wave functions canceling each other out, and that will form anti-bonding molecular orbitals. And that will be a node of absolutely 0 electron density. So that means the electrons cannot be between the nuclei. So these are two different ways that these, atomic wave functions can combine to form the molecular wave function. So here's a better picture, better drawing. So if we have the amplitudes of the wave functions being added, right, they're in phase. The crests are happening at the same point and the troughs are happening at the same point. They're being added together and they're getting, amplified, right? This would be constructive interference. And if we have the wave functions that are, out of phase, right, we have a crest and a trough and a crest, then they will cancel out. So this will be, essentially our bonding orbitals, and these are going to be our anti-bonding. Okay. So our atomic orbitals can mix together. They can make bonding orbitals. And like I said, that's kind of when they are in phase, right? The electrons in these orbitals are what helps hold the atoms near each other. That's why we call them bonding orbitals, because they are contributing to the strength of the bond. The anti-bonding orbitals are, those electrons, if you have electrons in those orbitals, they are pushing the atoms apart from each other. They are weakening the bond. So we want to have electrons, if we're going to form a really strong bond, we want to have electrons in the bonding orbitals, and we want to have as few electrons as possible in these anti-bonding orbitals. The non-bonding orbitals don't have any effect on bonding. They're not going to be super important in this class. They're going to be ones that you'll talk about in later classes, but we're mostly just going to deal with the bonding and the anti-bonding orbitals. And these molecular orbitals can be sigma bonds or they can be pi bonds. We've talked a lot about sigma bonds and pi bonds, right? If we have a single bond, then we're forming, sigma bonds. Those pi bonds are what we see when we have double and triple bonds. These molecular orbitals work just the same. They can have sigma, bonding properties, or they can have pi bonding properties. And we'll look at how that shows up. So in the atoms, electrons occupy atomic orbitals, right? So in atoms, we have atomic orbitals. In molecules, they occupy molecular orbitals, which are similar. They're just, slightly different, but they're similar in nature. So remember when we did these orbital diagrams were with the lines and the arrows, right? And we always had the lowest energy at the bottom and the highest energy at the top. We put 1 electron in each orbital before any could get 2. We had to fill up lower energy orbitals before we could go to higher energy orbitals. All of these rules still apply in molecular orbitals. Just now, we're going to take our atomic orbitals. We're always going to put our atomic orbitals on the sides. And then we're going to put our molecular orbitals in the middle. So this is for H2, so a diatomic molecule, homonuclear diatomic molecule. We are pretty much only doing homonuclear, which means that both atoms are the same. When atoms start to be different, it makes things a little bit trickier. Again, more on that in higher levels of chemistry. So this side is 1 hydrogen, right? This left side, this is 1 hydrogen, and the right side is 1 hydrogen. Each of those hydrogens has 1 electron in the 1s orbital, okay? When these atoms combine, they are always going to form 2 types of molecular orbitals. They are going to form a bonding orbital, which is our sigma, and they are going to form an anti-bonding orbital, which is our sigma star. The sigma is always going to be lower in energy than either one of the 1s. Bonding is a favorable interaction. So when we have our electrons, coming together to form a bond, right, that makes a lower energy molecular orbital. So these, the sigma molecular orbital will be lower in energy than the atomic orbitals. The sigma star, though, this one is our anti-bonding orbital. It will be higher in energy than either one of the atomic orbitals because it's weakening the bond. It's pushing the atoms apart. So when we fill in this molecular orbital, we're going to take, right, we have a total of 2 electrons. We have 1 here and we have 1 here. So 2 total in our molecule. So when we fill in our molecular orbitals, the electrons, right, we have to fill up this sigma bonding orbital before we can go on to our sigma star antibonding orbital. And remember, just in general, electrons can have, there can be 2 electrons in each orbital, right, on each line, essentially. So we put our 2 electrons in our sigma bonding orbital, and then we run out. We don't have any more electrons in our molecule, so there are going to be nothing in that sigma star. So let's see some more. So when we are forming these, right, we're having our 2 molecular orbitals that are being formed. We have that sigma, right, the sigma 1s, which is our bonding orbital, which again is lower in energy than our atomic orbitals, and our sigma star 1s, which is our antibonding orbital, which is going to be higher in energy than either one of our atomic orbitals. So when we get our in-phase overlap, that is when we are going to get the bonding, right, this one here. That's going to be our bonding molecular orbital. When we get the out-of-phase overlap, then we are going to get our antibonding. So remember we talked about when we had our bonding orbital, there was going to be a high density of electrons between the 2 atoms. So there are lots of electrons that can exist in that range, right? And here, since there's only 2 electrons total, that means 2 electrons could exist there and form a bond. But when we have the antibonding orbital, we see this nodal plane. And if you look, there's no electron density between those 2 atoms. It's completely empty space. And so this is weakening the bond. That out-of-phase overlap is pushing the atoms apart and saying that electrons essentially cannot exist between the atoms. So we want to have, electrons in our bonding orbital, but we would prefer not to have electrons in our anti-bonding orbital if our goal here is to make a bond. So when we are looking at hydrogen, right, hydrogen has 2 electrons in that bonding molecular orbital, that, sigma 1s, and no electrons in the sigma star 1s. So we're going to form our bond because we have electrons here, but not up here. And this will lead us to be able to calculate bond order soon. So here's another way of looking at it, right? If we have our 2 hydrogen atoms, they just have their 1s, they're just spheres. And when we add together our 1s, these are going to have a favorable overlap, right? If we have a bonding molecular orbital, the sigma 1s, they will have a favorable overlap and look like this, where we have, our 2 nuclei, and we've got, this region of electron density where, electrons can exist between the atoms. If we have our antibonding sigma star 1s, we are going to get the nodal plane. And so then no electrons can exist between the 2 atoms. So here we have our nuclei, right? And all of the electrons are existing in the space, not, between the atoms, rather than existing mostly between the atoms, like in the bonding molecular orbital. So here down at the bottom it says the sigma star 1s molecular orbital has a nodal plane bisecting the internuclear axis. So going right through those 2 nuclei. A node or nodal plane is a region in which the probability of finding an electron is 0. So you're going to need to be able to draw these be able to recognize what they look like. So our isolated hydrogen atoms are going to be a circle with just a dot in the middle showing the nuclei. When we have the bonding molecular orbital, we are showing that the electrons can exist between the nuclei, and the anti-bonding, the sigma star 1s, is showing that nodal plane where the electrons, can't exist between the 2 atoms. So be able to draw these. So here is our molecular orbital diagram for H2. Again, we need to follow all of those rules that I have there on the left, the off-bow principle, the Pauli exclusion principle, and Hund's rule. Those were all of the rules that we learned about when we were filling atomic orbitals. We are now going to apply them to filling molecular orbitals. Again, molecular orbitals are filled in order of increasing energy. So you're always going to fill the lowest energy first and go up from there, filling in the ones right closest to the nucleus. The Pauli exclusion principle says that you can have 2 electrons per orbital, and they need to have opposite spins. And then Hund's rule says we need to fill each orbital with electrons of parallel spins, right? They're all going to be spin up or they're all going to be spin down before completely filling an orbital. So we're going to put one electron in each of these degenerate orbitals before any will get two, and before we can move on to that next energy level. So this is what's new though, this bond order. Bond order is going to be half the bonding electrons minus the anti-bonding electrons. So you're going to do bonding minus anti-bonding times 1/2. Okay, so I'll show you how that works. So here is our molecular diagram for hydrogen. So, going in order of increasing energy, always going from the bottom up, we have, one of the hydrogens has 1 electron in the 1s. The other hydrogen has 1 electron in the 1s. And we're putting them parallel because they're both, the same. So then we can draw in our molecular orbitals. So we have down at the bottom, we have our sigma 1s, and at the top we have our sigma star 1s. Again, the sigma 1s will be lower in energy than either one of our 1s atomic orbitals, and the sigma star 1s will be higher in energy than either one of our atomic 1s orbitals. Okay, so we can fill those in, and we have a total of 2 electrons. So those 2 electrons are both going to go in that sigma 1s, in that bonding, molecular orbital. And then we've run out of electrons. There's none to go up in that sigma star 1s. So when we calculate bond order, the way that we do that is we do, bonding minus anti-bonding. So 2. These are our bonding electrons, right, because they are in the sigma, so that's 2, and our anti-bonding, right, is 0. There's nothing up here. So we go 2 minus 0 multiplied by 1/2 gets us 1. And so this bond order tells us, a bond order of 1 tells us that H2 is making a single bond, which should make sense, right? If we were going to draw H2, we would draw it like this. There's a single bond between those 2 hydrogen atoms. If you had a bond order of, 2, that would be a double bond. A bond order of 3 would be a triple bond. So that bond order is telling you essentially how many bonds are formed between those 2 atoms. So here's some more about bond order. Again, it's going to be bonding minus anti-bonding, and then we'll multiply that by 1/2. Usually, most times, the bond order corresponds to the number of bonds described by valence bond theory. That's just kind of our, typical drawing Lewis structure theory. A bond order equal to 0 indicates that there are the same number of electrons in bonding and anti-bonding orbitals. And this essentially means that the bond will not happen, right? If you have a 0 bond order, that's telling you they will not form a bond, okay? Because the amount of electrons that are trying to form the bond are equal to the amount of electrons that are trying to push the atoms apart. And so they're going to kind of cancel out, and the bond won't happen at all. This one, the one I have in bold, the greater the bond order, the more stable the molecule or ion. So this is telling you the bond order of 2 or 3 is going to be more desirable than a bond order of, let's say, 1 or 0.5. You can have decimals, you can have fractions here. So we're just looking at greater bond orders to tell us more about the stability of the bond. And that should also follow that, then the weaker, or the smaller the bond order, the weaker that bond is. And also this will follow that the greater the bond order, shorter the bond length, greater the bond energy, right? Because if, say, we had a bond order of 2, that would typically correspond to a double bond. And if we're comparing that to a bond order of 1, a single bond, right? The bond order of 2, that double bond, is going to be shorter in bond length, greater in bond energy, just like we've learned thus far in the class. So I'm going to, draw the molecular orbital diagrams for He2 1+ and He2 to see if these molecules would happen. What is their bond order? Will a bond form? And, if so, how strong is it? This is going to be done exactly the same way that we did the molecular orbital diagrams for hydrogen. So if you feel confident and you want to try it out, you can go ahead and pause here and try to fill this in. Remember that He2 1+ means that one of those hydrogens has lost, heliums has lost an electron. And then, He2, then they would both have both of their electrons. So if you'd like to try and do this, go ahead. If you want to see one, then you can pause and try and do the second one. So here we go. So we have an atomic orbital of helium, right? And helium has 2 electrons in the 1s. And then if we have the other one as He+, then it's lost one of those electrons. Normally it would have 2, but since it's He+, it's lost one. And we can go through then and fill in our molecular orbital diagram for He2 2+. So they are going to form, a sigma 1s that is lower in energy, and we will also have a sigma star 1s that is higher in energy. Total here in this structure, we have 3 electrons, 2 over here and 1 over here, so we need to put 3. So 2 of them will go in the sigma 1s, and then that sigma 1s is full, and that last electron will go up in the sigma star 1s. So we have 2 electrons in the bonding orbital and 1 electron in the anti-bonding orbital. So when we calculate our bond order, it's going to be 1/2, right? We're going to have 2 electrons in the sigma 1s minus 1 electron in the sigma star 1s, then multiplied by 1/2. So we have a bond order of 1/2. So this molecule could exist, right? He2 2+, but it would be a fairly weak bond that's holding it together. Bond order of 1/2 is really not desirable. So there, it's a fairly weak molecule. And then if we look at He2, so we have 2 electrons in the 1s for each of those helium atoms. And helium is a noble gas, right? It's following the duet rule rather than the octet rule, but its 1s is completely full. And so if, thinking about what we know about helium, we know helium doesn't make molecules. Helium is not one of our diatomics that we've had to remember, so this should strike you as weird in the first place. Use your logic when you're thinking about these, right? You've never probably heard of He2, and there's a good reason for it. Right, so we have 2 electrons in each of the 1s, and again, they're going to form these molecular orbitals. We have the sigma 1s and the sigma star 1s. Both of them, right, we have 4 total electrons, so we go, 1, 2, 3, 4. So we've put our 4 electrons in our molecular bonding orbitals, and we see that we have a bond order of 0 because we have 2 in the bonding orbital, right? 2 in the sigma 1s, and 2 in the anti-bonding orbital, the sigma star 1s. So we do 2 minus 2 times 1/2 gives us 0. So remember, a bond order of 0 tells us that this molecule does not happen. There is no bond that is being formed. So He2 1+, yeah, that'll form a really weak bond, but He2 will never form. That's going to be a bond order of 0. So here's another one. Use molecular diagrams to predict whether H2 1+ and H2 1- exist. Determine their bond orders and electron configurations. And so we haven't talked about the electron configurations yet, but I would encourage all of you to pause here and try to do the molecular orbital diagram for H2 1+ and H2 1-. Fill in those molecular orbital diagrams, calculate the bond order, and figure out, would those exist? And if so, what is their, what's the strength of those bonds? And then after that, come back, press play, and I'll go through the answer, and then we'll talk about the electron configuration. All right, going through the answers. So it's going to follow that exact same stuff that we did for just H2 and He2 and all of that good stuff. So if we are going through this, our atomic bonding orbital for hydrogen is going to have 1 electron, and our atomic orbital for H+ will not have any electrons whatsoever. And so we only have 1 electron for our molecular orbital, and so we're going to put 1 electron down in that sigma 1s. So if we're going to go through and calculate the bond order, we have 1 minus 0 times 1/2 will get us just 1/2. So yes, the bond will form, but it's going to be a fairly weak bond. And if we think of H2 1-, that means one of our hydrogens has, just the one electron, and the other one has gained an electron, and now has two. So we have a total of 3 electrons that we can use in our molecular orbital diagram. So 2 of them will go in the 1s, that sigma 1s, and one of them will go in the sigma star 1s. So when we are calculating our bond order, we're going to do 2 minus 1 times 1/2, which gets us 1/2. So these actually have the same bond order. And again, they're both fairly weak. This is why we don't typically see these molecules, H2 1 plus or H2 1 minus, because they are very, very weak molecules. And so then, if we were going to go through and write their electron configurations, we would write this as sigma. So this one has sigma 1s, and in the sigma 1s, there is 1 electron. And that's it. That's the electron configuration for H2 1 plus. If we look at H2 1 minus, we have sigma 1s, and there are 2 electrons in the sigma 1s, and then we have sigma 1s star, and there is 1 electron in that sigma star 1s. So that's how we write them. We put the name of the orbital or the title of the orbital in parentheses, and then the number of electrons in that orbital will go as a superscript on the outside of the parentheses. So that's how we're doing the electron configuration. So here are bonding in the S block. These are homonuclear diatomic molecules. But now we're not just using the 1s, now we're using the 2s. But they're going to be exactly the same because we're still just dealing with s orbitals, and we're still just using valence electrons. So even though lithium has, 1s2, 2s1, right, we only care about the valence electron, so we're really just looking at that 2s1. So the way it would look for lithium, right, Li2, each one of those lithiums has 1 electron in the 2s. And so they are going to combine, and they are going to form a sigma 2s and a sigma star 2s. Okay, just like we did for the 1s. This molecule has a total of 2 electrons. So both of those electrons are going to end up in the sigma 2s. There's going to be nothing up there in the sigma star 2s. And so then if we went through and calculated the bond order, right, lithium's bond order would be 1. We would do 2 minus 0 times 1/2 gets us 1. If we looked at beryllium, Be2, both berylliums have 2 electrons in the 2s. Again, we're not worrying about the 1s electrons because they're not valence electrons. So just like lithium, this is going to form a sigma 2s and a sigma star 2s. And when we do this, right, we have 4 total electrons, 2 from each of the berylliums. So 2 electrons will go in the sigma 2s, and the next 2 electrons will go in the sigma star 2s. So when we go through and calculate the bond order, we're going to do 2 minus 2 times 1/2 gets us 0. So this molecule will not happen. So Be2 won't form a bond, right? We won't have that, but Li2, that could happen. And that would be single bonded. So we would form, this molecule, but not the other. Okay, so again, you can look at bond order to tell you, will the molecule form? How strong will that bond be? All of that good stuff. So, just using energy diagrams, molecular orbital theory, you're going to draw or select the appropriate molecular orbital energy level diagram. So the reason that I say it this way is because we're going to get into this, when we get into the 2p's, right, the pi bonding, things can be in different orders. And so that's why I say draw or select the appropriate molecular energy level diagram, because it's a little bit confusing when you're first going for it. The molecular orbital diagram for boron, carbon, and nitrogen follows a different molecular orbital diagram than the one for oxygen, fluorine, and neon. So you're going to need to know the difference and memorize the order. But for now, I would just focus on being able to fill them in. But for the tests, you will need to know the order of those energy levels. So you're going to draw or select the appropriate molecular orbital energy level diagram. Again, select the one that has them in the right order. And then you're going to determine the total number of electrons in the molecule. Again, this is going to be all of the valence electrons. And then you're going to add these electrons to the energy level diagram, putting the electrons in the lowest energy level first before we go on to the next and to the next. And again, electrons must occupy all the orbitals of the same energy singly before pairing. So one electron in each before any get two when we get to degenerate orbitals. So here's some kind of just in general trends that you should have started noticing. The bonding molecular orbitals are going to be always lower in energy than the anti-bonding molecular orbitals. And since 2s atomic orbitals are lower in energy than 2p's, like when we draw that, right, we would draw the 2s lower than the 2p. The 2s molecular orbitals will also be lower in energy than the 2p molecular orbitals. So that's the same. So when we do individual atoms, the 2s is lower than the 2p. When we draw molecules, the 2s is still lower than the 2p. Nothing changes there. For number 3, the sigma 2p is lower in energy than the pi 2p, and the sigma star 2p is the highest molecular energy level. So that's going to be a good one to remember. Things in between those can kind of shift around, but the sigma 2p is always going to be the lowest, and the sigma star 2p is going to be the highest. This is like usually. This can sometimes change. The sigma star 2p, though, always the highest. That's a good one to remember. This one is more like a usually. You'll see. You'll see soon. And then side-to-side overlapping p orbitals have the same energy in both the bonding and anti-bonding. So we're going to get to that soon as well. So here we go. If you have this side-by-side overlap, right, where we have the p's are both going in the x direction, the way that they add together is they're going to combine these, and we're going to get a region of lots of electron density in the middle. That will be the shape of the sigma 2p molecular orbital when it is a bonding molecular orbital. And when we have the sigma star 2p, we're going to get the nodal plane. Essentially, you can just think of these as being, spun one way or the other, right? They flip to form the bonding, or they flip to form the anti-bonding. So then we are seeing the nodal plane. There are no electrons that are going to exist in this space between the two atoms. If we are adding them, more up and down, we will see this, which is what we kind of see a lot, right? We were drawing the flower diagrams. This should look familiar. This overlap of the pi 2p, where the electrons exist above and below the plane. And so that would be when we have our bonding molecular orbitals. And then our anti-bonding molecular orbitals will be this nodal plane again. And we have, the dumbbells are kind of bowing away from each other. So I would be able to recognize what these look like, be able to draw them if asked. So these are the different bonding and anti-bonding orbitals of the p orbitals, whereas the other ones we were looking at earlier were for the s orbitals. So this is what it looks like for oxygen. Most times we won't include the stuff down here. All of this is the 1s. Usually we'll just include the stuff above the line I just drew. That'll be for the 2s and the 2p, since we're mostly just looking at valence electrons. You can include the 1s if you like, but unless I say like include all of the electrons, you're just responsible for including the valence electrons. So we have, if we think about oxygen, each oxygen, that'll be on this side, right, and this side. So each oxygen will have 2 electrons in the 2s, and then it will have 4 electrons in the 2p, because we know oxygen has 6 valence electrons. So we do that for both sides. 2 electrons in the 2s, 4 electrons in the 2p. And then the thing that's new is this mess in the middle, where we have the bonding and anti-bonding orbitals. So if you'll look, we already learned how to do this part. Okay, The 2s orbitals will form a sigma 2s here and a sigma star 2s here. The sigma 2s will always be lower in energy than the 2s orbitals, and the sigma star 2s will always be higher in energy than the 2s orbitals. So we have 4 electrons total, 2 from each of the 2s's. So we put, 1, 2, 3, 4. The thing that's new now is we are going to look at how to do this stuff in the 2p. Okay, so I'll talk about that now. So if we look at the 2p, on this side, this will be the one for oxygen, fluorine, and neon. Okay, we are not getting the 2s, 2p mixing. Okay, and so what that means is we have the sigma goes on the bottom, and the pi is higher than that. And then we've got the pi star and then the sigma star. So it's going to go sigma, pi, sigma. Okay, the other way that they can happen is for boron, carbon, and nitrogen. We do have 2s, 2p mixing. And so all that means for the level of this class is that these on the bottom get flipped. The sigma 2p is now higher in energy than the pi 2p. I don't need you to know why this happens. I just want you to know that it does, and know the order. So like this, this order happens for these elements, and this order happens for these elements. When you get into higher levels of chemistry, you can talk all about why they do and all of that good stuff. But for the level of this class, I just want you to know which order goes with which elements. Okay, and then be able to use that. So boron, carbon, nitrogen, they're on the left. If we don't have 2s, 2p mixing, then we go sigma 2s, sigma star 2s, and then it goes pi 2p and sigma 2p. And so when we have the pi 2p, we have two lines that we're going to put. And then sigma 2p and then pi star, again, we're going to have, 2 lines. And then sigma star. And then again, these get flipped over here. So the things that are different are these. Okay, for boron, carbon, and nitrogen, we go pi and then sigma. For oxygen, fluorine, and neon, we go sigma and then pi. You are going to want to work out lots of these problems. If you pop over to what is this? Chapter 10 lecture worksheet. It's going to be problem 28. I would encourage you to try those problems out. It will have you go through writing the molecular orbital diagrams for N2, N2 1+, O2, O2 1+. It'll have you write the electron configurations, determine the bond order, and talk about all of those things. But again, you need to know this order. Otherwise, all of the same rules apply. You need to fill in, the sigma 2s before you go to the sigma star 2s, and then fill in the pi 2p before you go to the sigma 2p. And just be careful, like I said, that there are 2 lines that you're going to draw for all of the pi's and pi stars, whereas we were just drawing 1 line for the sigma and sigma stars. And you're going to put, 1 electron in each before any get 2, all of that good stuff. So try some of these out. These are real tricky to get the hang of. Especially try these out on paper before you move on and try to do it in ALEKS. It is much more challenging to try and do it on the computer in ALEKS if you have not tried to do it on paper yet, I promise. So don't just skip ahead and try and get your homework done. Put in the practice to get really, really good at these before going on. And as always, I'm available if you have any questions. And that is the end of Chapter 10. We are nearing the end of the class, just 2 more chapters to go. Keep it up.